Welcome back to the second part of the chapter 2 video. In this part, we're going to be looking at chemical formulas and that nomenclature that I promised you at the beginning. First of all, so let's take a look here. A molecular formula is a representation of a molecule or a compound which consists of the following: chemical symbols and subscripts that tell you how many there are in a molecule. Sorry, or the ratio in an ionic compound. Oh, well, molecular formula. Okay, so just in a molecule. A structural formula is going to show you a couple other things. So it shows you structurally what's going on here. So right here we have CH4. This is methane. Okay. Okay, this is methane. All of these are methane, and they're different representations of that. So this one right here, A, is our molecular formula. And this structural formula is, you could call B. Okay, and this sort of shows that. And then C and D show a little bit more, so we're not really going to get to it until later in the chapter, but this shows C and D sort of show the structural formula in terms of its shape. Okay. Okay, so now let's take a look at a few things. So elements that exist as molecules. All right, so what does that mean? Many elements consist of just discrete individual atoms: carbon, magnesium, silicon, carbon. They exist as individual atoms, and they can form these neat lattice structures and things like that. But some elements only exist as molecules, okay? And the most common ones of these are the diatomics, okay? And I've actually memorized these. You don't have to memorize them, but you should definitely have them written down. You will never see hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, or iodine written by themselves, not attached to anything else. So if they're not attached to another element, they're attached to themselves in these diatomic setups. So here, this you'll get some more. The most common form of elemental sulfur is actually S8. A common form of elemental phosphorus is P4. So you're going to see that a lot. But these diatomics, these are things that you definitely need to know. And to sort of look at that, so one hydrogen atom all by itself is right here. Okay, well, and that one hydrogen atom, you're not going to see that. Yeah, it's all by itself, you won't see it. Two hydrogen atoms, you're also not going to see that. But you will see a hydrogen molecule, an H2 unit. And usually it might be written as H2G with a gas to indicate that it's a gas if you're in a chemical equation. Here you have two H2, and again, it might be with the gaseous symbol afterwards, okay? And that indicates two hydrogen molecules. All right, so now let's take a look at what's called an empirical formula versus a molecular formula. So actually, let's start down here with the molecular formula first. It tells us that a molecular formula indicates the actual number of ions. Day is a day for interruptions. Sorry. Okay. A molecular formula indicates the actual numbers of atoms of each element in a molecule of the compound. Okay, so let's take a look at that. Let's look at benzene. Okay, C6H6. So benzene looks a little bit like this. Okay, and there's a hydrogen off of each one. Now, if we say put some benzene through a mass spectrometer and or just look at things, and what we find is that we have an empirical formula which indicates the simplest whole number ratio of the numbers of atoms or ions. Okay, now the empirical formula is a simplified ratio. And the importance of this simplified ratio is that whenever we do a test to determine what we have, it will come back to us as a ratio, whether we do a mass spec or whether we're interpreting in an MR. It's going to show us this ratio. It's not going to actually tell us that there's 6 of each one. It's going to tell us that we have a 1-to-1 ratio. Or in this case, we have a 1-to-1 ratio here. So now here we have hydrogen peroxide, H2O2, and that will look like this. Okay, but you can see then that the simplified ratio for that is just H to O, 1 of each. Another option here is that we have isomers. Okay, it may be possible for the same atom to be arranged in different ways. Okay, so we have 2 things. We have acetic acid and methylformate, and they have the same molecular formula, 2 carbons to 4 hydrogens to 2 oxygens. Okay, so in order to tell the difference of those, methylformate is written C2H4O2, and acetic acid will be written as HC2H3O2, and we write it like this because it shows the acidic proton out front. In this class, this is how I want you to refer to acetic acid. Okay, now let's take a look. This is a periodic table, and this is just another periodic table, a little different than the one that I made you print because it's all in color. I'll probably make this one available as well. I know that not everybody has a color printer, so that won't be, but if you have a color printer, this is a really, really great one to print because it has, the groups listed on it. Okay, and you'll see this later in a later slide as well, but here you can see the here you can see the alkali metals right here, and those are in orange. Ooh, there we go. And here's the key here that tells you that they're alkali metals. All right, and then here in yellow, I won't do that for everyone. You can see the alkaline earth metals here. Okay, and then here, I'm going to come all the way over here now. You can see the reactive non-metals in green. These, all the ones in green are reactive non-metals. Your metalloids here in kind of a greenish blue, and your post-transition metals underneath in just a little bit of a slightly different blue. They show them here together. Your transition metals here in pink. Okay, and your lanthanides and actinides down below. Okay, now when you're looking at this, here you can see the atomic number on top. That should be atomic number. And then the symbol, the name, and the weight, or the molar mass, or the average atomic mass. Okay. Metals are shiny, malleable, good conductors of heat and electricity. Okay. And let's add to this that metals lose electrons to form cations. Okay. Non-metals appear dull. They're poor conductors of heat and electricity, and they will often gain electrons to form anions. And then metalloids are interesting, but metalloids will go either way. So it can be kind of tricky. They conduct heat and electricity moderately well. They possess some properties of metals. So you kind of have to look at them and say, okay, well, which way are they going? Are they going in the direction of the nonmetals, or are they going in the direction of the metals when it comes to forming cations and anions? Okay. So this just shows sort of what I was referring to on the previous periodic table. We have alkali metals, alkaline earth metals, transition metals. They call these pnictogens, and you don't see that so often. So this is your group 1, group 2. This will be called group 13 or group 3A, 4A, 5A sometimes, 6A, and 7A, and group 8A. Sometimes with the A, sometimes without. These, they list these, but nobody refers to these by these group numbers, okay? They're just referred to as your transition metals. And transition metals are interesting because they can form a variety of different cations. All right, now let's take a look at predicting what we're going to have. So you have that periodic table. Remember, it was a requirement that you print it. If you don't have the super colorful one with everything color coded, I recommend that you color code, use some crayons or colored pencils or markers or something, and that you color code this one. Okay, and so all of your alkali metals, that's group 1, not hydrogen. Hydrogen is not a metal. That's an important thing to remember. They lose 1 electron to form a cation with a 1+ charge. All of the alkaline earth metals lose 2 electrons to form a cation with a 2+ charge. Okay, and then we have those non-metals. Our halogens, group 17, often these are also called group 7. Because until recently, they never used to number the groups in the transition metals, which I think is smart because they don't follow the same patterns that you see. Okay, so group 7A, the halogens, they gain 1 electron to form an anion with a 1- charge. And group 16, okay, we can also call that group 6A. A lot of times I think of this as the oxygen group. Okay, and they gain 2 electrons to form an anion with a 2- charge. All right, so now here's just a sort of a graphical image of what kinds of ions they gain and lose. So here you'll find, here we have our alkali metals here. And you can see they all form a +1 charge. And then we have our alkaline earth metals here in the second column, group 2, and they all form a 2+ charge. Now we can come over here and we can see aluminum here with a 3+ charge. Here they have carbon listed as a 4- charge. You don't see that very much. I'm just going to do this so that you're not looking for it. Okay, it's kind of rare. And then we're going to think about these in terms of group 5, 6, 7, and 8. Okay, and here we have, you can see that in group 5, our nitrogen group, these all form -3 charges. And here in group 6, then we have all of these with, -3 for group 5, -2 for group 6 with our oxygen. And then here you can see your noble gases, and these are all neutral. So no charge, and they don't form ions, no ions. And then here we have our halogens all with a -1 charge. Now let's take a quick look over here now, and you will see right here, see how these all form varying charges. Okay, and I've kind of come over here too, like kind of messily, but it's there as well. Everything kind of in here, we often call these type 2s because most of them will form variable charges. And this just means that sometimes they form more than 1 ion. Not all of them. But sometimes they'll lose 2 or 1 or 3 or even 4 electrons to form those positive charges. Okay, so now let's take a look at polyatomic ions. In this case, and don't worry, at some point in time, I'll stop telling you about them and we'll show you how they work. All right. Actually, before I go on, let's take a look here, and I want to show you the ion list that we have. So hopefully you guys have all printed this, and let me make it a little bit bigger. Here you can see this okay, you should have all printed this, and this shows a whole variety of things. So let's take a look here for a minute. Here we have right here. Okay, these are common monatomic cations and anions. And what that means is that they only form one type of ion. Well, hydrogen actually can also form a hydride with a negative. So the one exception to that is that you can have an H plus for hydrogen and you can have an H minus for hydride. And you can see that for the common monatomic cations that we were just looking at with the alkaline earths and the alkali metals and a couple of others tossed in there, you can see a bunch of them. So here you can see your alkali metals, and then you can see your alkaline earth metals here. And I don't have them in total order. And then you can see a couple of these kind of that group five-ish. No, sorry, not group five, group three, looking at it wrong. Okay, and these only form one type of cation. And then down here, we have the common monatomic anions, and these only form one type of ion. Chlorine only becomes chloride, iodine only becomes iodide, sulfur only becomes sulfide, like this. And that's how they form those. Okay, now, if you scroll down here, you can see these common type 2 cations. And here you can see a list of the, here you can see a list of some of those transition elements and the different types of ions that they'll make. So here you can see iron 3 and iron 2. And so this first one has lost 3 electrons, and this one has lost 2 electrons, and copper 2 and copper 1 and cobalt 3 and cobalt 2. You'll find down here a few of them, and that is silver, cadmium, and zinc. And silver, cadmium, and zinc each only form one cation. And if you look at them on the periodic table, you can see right there silver, cadmium, and zinc, and they form this little block like this, where you have the zinc here and then the silver and the cadmium. Okay, and this little block here forms the what you see here, and it only forms that you don't have silver 1 and silver 2, or zinc 1 and zinc 2. And you'll notice that none of those have Roman numerals. So here you have silver with a +1 charge, and zinc and cadmium each with a +2 charge. Okay, and you'll notice, remember we said that they can form different ions, and we identify the charge with a Roman numeral. So Fe3+ is iron 3, and Fe2+ is iron 2. And so what's in parentheses here, this Roman numeral, tells you which of the ions it is in that transition metal. And it's only right if you include it. That's very, very, very important. All right, now on this side of things, we have common polyatomic ions. So there's only 2 common polyatomic cations. One is ammonium and the other one is mercury 1. And so mercury 1 is kind of on here twice. And the reason for that is that mercury 2 is Hg with a 2+ charge on it. It's one mercury atom that has lost 2 electrons. Mercury 1 is 2 mercury atoms that are stuck together and have each lost 1. So it's never listed as Hg1+, because mercury 1 is always like a diatomic cation. So it's always Hg2 with a 2+, and you have to keep that 2 on there all the time with that. It's sort of like peroxide, O2, 2-. Okay. And then we have the common polyatomic anions. Okay, and the common polyatomic anions are really long. You can see them all right here. Okay, so pay really, really, really close attention to the way that they're spelled and what we have here. All of these are IUPAC names, the names that you have to learn. The only one is hydrogen carbonate, HCO3 with a 1- charge on it. Here is written as bicarbonate. Okay, and bicarbonate, you will often see that. It's the only time where you'll routinely see a common name. Okay, so let's come back to our periodic table and start our slideshow again. Okay, so here we have, this is the ions that we've discussed so far called monatomics. Okay, so I showed you the polyatomic ions. They're electrically charged molecules, a group of bonded atoms with an overall charge. Okay, and then oxyanions are polyatomic ions that contain one or more oxygen atoms. Okay, so we can see all those. One example of both a polyatomic ion and an oxyanion is, let me pick a good one for my, we'll look at, that one's hard. Let's look at a couple. First of all, let's look at ammonium. Okay, and this is one of our only polyatomic cations, and it is NH4+. And what it really is you take ammonia, and don't worry about how you draw these. When we do those, you'll find out, okay? And we take, so here's ammonia, and you've all heard of ammonia, okay? And what you do is you take an H+ and add it on. So instead of those dots there, now you have another H. And that means you have that H+, so the whole thing has an overall positive charge on it. So what's in here that you can see, and I'm sorry, I sort of ran them together, is you have a molecule, NH4, and the whole thing together carries a +1 charge. So it moves around as a group. You can't take the NH4 and split it up into different pieces. The same thing is true with, we could say, for example, peroxide. Okay, so let's look. So here we have oxygen gas. Okay, hang on. Let me turn on my annotations. We have oxygen gas, and oxygen gas is O2, and it looks like this. Okay. This is oxygen gas. It's neutral, and it's O2. Now you also have peroxide. And actually, you know what I'm going to do? I am going to take these off, because when we're doing Lewis dot structures, we don't draw them around molecules. So this is the molecule for oxygen gas, O2. Peroxide is O2 with a 2- charge on it. So you take those oxygen atoms like this, and it ends up with an additional couple of electrons, okay? And this O2 unit functions together. So you could make hydrogen peroxide, H2O2. I showed you that on a previous slide. And then you have this. Okay. All right. Okay, when electrons are transferred, ions form and an ionic bond results. Ionic bonds are electrostatic forces of attraction. When electrons are shared, molecules form and a covalent bond results. Okay, compounds are either ionic or molecular, covalent. Okay, so an ionic compound is a compound. Okay, so we have ionic compounds, and they're only called ionic compounds. Molecular compounds, so I'll say only. Molecular or covalent compounds are also called molecules. All right, and so that means that you can have a molecule of water. All right, let me fix that. You can have a molecule of water. You can have a molecule of CO2. You can have a molecule of benzene. You can have a molecule of hydrogen peroxide. And notice with all of these molecules, we have no metals. So molecules are always non-metals. Am I going to run out of space? Okay, and that's really important. Molecules are always non-metals. So let's come over here now and let's change this to, we'll look at our ionic compounds. I'm going to change the color on that, ionic compounds, so that we can, okay. Ionic compounds always have a metal cation with an anion. You have to look for that metal. And so examples of that might be sodium chloride, calcium chloride, might be magnesium sulfate, okay? And notice that each one of these begins with a metal. We have an alkali metal and we have a couple of alkaline earth metals, okay? They always begin with a metal, and that's kind of how you tell them apart. Now, you don't have a single molecule of sodium chloride, and you don't have because it forms these kind of never-ending blocks. Okay, so let's take a look first at our ionic compounds. Metals readily lose electrons to form cations. Non-metals readily gain electrons to form anions. When a metal and a non-metal react, transfer of electrons usually takes place. Metals and non-metals generally form ionic compounds. So I'm going to actually say metals plus non-metals. So you have to put them together. That's kind of what that means. A metal and then a non-metal. A compound that contains ions and is held together by ionic bonds is called an ionic compound. All right, now let's take a look at some formulas. Okay, ionic, now so what I want you to do next, I don't have it in front of me, but remember that ion list? Go get it. If you don't have it, go get it. You're going to need it. Okay, now I'm going to pretend for the rest of the lecture as though you have your ion list and your periodic table sitting right in front of you. Okay, so ionic compounds are overall neutral. The formula of an ionic compound must have a ratio of ions such that a number of positive and negative charges are balanced. Okay, so what does this look like? Well, for example, if we take Al3 plus and O2 minus, forms Al2O3. So where do we get that? Well, there's two different ways of doing it. We can say, first of all, we have to be balanced. So we can have Al3 plus and then O2 minus, but now we have 3 positive charges and 2 negative charges. So let's add another O2 minus. Well, now we have 4. Okay, now we have 6. And if I add another oxygen, now I have 6 negatives. So 3 positives here. So I have 1, 2, 3, 4, 5, 6. And those positive charges are balanced out with my 6 of these here. So here I have my 6 positive charges, and here I have my 6 negative charges. Kind of a quick way of doing that is to say, okay, well, if I have my aluminum ion and I have my oxide ion, I can just bring these numbers down, Al2O3. So you can think about it in either way. Okay, now let's take a look next at our ion list, and let's look for lithium. Lithium becomes Li plus, and sodium becomes Na plus, and magnesium becomes Mg2 plus. And right now I'm looking at the ion list, that common monatomic cations. And now let's take a look at the anions. Oxide is O2 minus, and chloride is Cl1 minus. And we don't usually write the 1. If there's no number there, it means only a single charge. You might say, well, how come the plus or the minus, the positive or negative, comes after the number? The reason it comes after the number is that that allows us to differentiate between a charge and an oxidation state. So if the plus or the minus comes first, so -2 minus +2, that indicates what's called an oxidation state. And we'll learn about that in the chapter where we learn about redox. Okay, now let's see what happens when we put these together. So first of all, let's take this lithium and this oxygen. So we say Li plus and O2 minus. Now we need 2 positive charges to balance out our 2 minus charges. So this becomes Li 2O. Okay, now let's see what happens if we take lithium and chloride. Well, these are balanced 1 to 1. So we would just say LiCl. Now let's take a look at magnesium over here. We have magnesium, okay? And let's take a look at the magnesium with the oxygen. So we have Mg2 plus and O2 minus. Well, look at that. 2 positive charges balance 2 minus charges. So this just becomes MgO. Okay, we wouldn't want Mg2O2 because that would not be correct. It wouldn't be the lowest possible thing that we have. If we had MgO2, then it would be a magnesium peroxide. Okay, but this is magnesium oxide. And now we can say, well, let's combine Mg2 plus and our chloride, Cl minus. And if we have 2 positive charges, we need 2 negative charges. And so this becomes MgCl2. Okay, so now we have, more formulas of ionic compounds. And these, now what we're going to do is we're going to make some compounds, or we're going to make a compound where we contain polyatomic ions as the cation, the anion, or both. And the polyatomics end up forming discrete units. So you see here we have that Ca2 plus and the PO4 3 minus. And you can observe that you have to make 6, or you can bring this down, the 2 down here and the 3 down here. And you have Ca3PO4 2. Now, do you see these parentheses right here around the phosphate? Okay, those parentheses have to be there. If you do not include the parentheses, it is wrong. Okay, so you must include the parentheses. The parentheses tell us that the phosphate is acting as a distinct unit, and you have 2 of them. Let's look at another option. Let's take a look at hang on. I don't want to get ahead of myself, but I also don't want to forget something. Okay. All right, so now let's take a look at a couple of other things. If we look at our ion list, remember that we had 2 different possibilities for copper. Okay, we had copper 1 and we had copper 2. Oh, that's awful. And copper 1 is Cu with a 1 plus, and copper 2 is Cu with a 2 plus charge. Now let's combine these with nitrate. Nitrate is a really, really cool anion. It's soluble in almost everything, so it's really, really useful, and you will see it a lot. And the nitrate anion that you see in those polyatomics is NO3 with a 1 minus. So if you combine your +1 and your -1, then the copper 1 nitrate is just equal to CuNO3. And copper 2 nitrate, okay, well, now we have that 2 plus, so we need two nitrate units. This becomes Cu, and now we need to tell us that there's 2 nitrate units, CuNO3 2. Okay, now let's take a look at molecular compounds, and we're going to be practicing a bunch of these in just a bit. Okay, now molecular compounds or covalent compounds, remember, these result when atoms share electrons. They exist as discrete neutral molecules, and they're always a combination of non-metals. This is kind of your clue that you're working with something that's molecular. They often exist as gases with low boiling point liquids or low boiling point solids, like there are different kinds of water. So water is a gas, water is liquid, water is ice. Okay, now let's take a look next at chemical nomenclature. Nomenclature is a collection of rules for naming things. Compounds are identified by both their formula and their name. So remember from that previous slide where we had this formula, CuNO3, 2. Okay, and the name that went with that was copper 2 nitrate, and they mean the same thing. We will learn how to name the following types of inorganic compounds: ionic and molecular binary compounds composed of 2 elements, ionic compounds containing polyatomic ions, acids, and there's one more in here that didn't make this list, and that is hydrates. Okay, so let's start with naming ionic compounds, and we're going to look at some simple ones. Name the cation first, followed by the name of the anion. A monatomic cation is just given the name of the element. A monatomic, that's a typo, it should be monoatomic. The monatomic anion is given the name of the element with its ending replaced by the suffix "ide." And a polyatomic ion is just given the name of the ion. Okay, and so we did a couple of those. Remember, we showed here, we showed MgO. Well, this came from magnesium 2+ and O 2-. This is the magnesium ion and the oxide ion. Okay. And now if we wanted to, here's, let's look at another example. Let's say that we have, we'll go with a nice tricky one. Let's do SN, three P, I want to grab the right one here, 4. Whoa. Okay, so I would look here and let's say, okay, how do we determine this? And so you work your way backwards. That 3 there means that you probably have a 3- charge up here. And this 4 probably means that you have a 4+ charge up here. So that means that this SN3P4 is made of an SN4+ and a P3-, and you need that in order to find this. So then you look on here and you see SN4+ is tin 4 and P3- is phosphide. Okay, now let's take a look at it in terms of polyatomics. Okay, so let's say that we have Fe C2H3O2 2. All right, now I take a look here and see how there's nothing here. So that means that there's one of these. So I can bring this up and that forms a 1-, and I can bring this 2 up and I have a 2+, and that tells me what I'm working with. Fe2+ is iron 2. Okay, and C2H3O2 1- is acetate. Iron 2 acetate. Okay, let's do one where we go in the other direction. Okay, so let's say that we start with, I don't have these notes, I'm making them up as I go, which is always kind of fun, actually. Let's say that we have magnesium hypochlorite. Okay, well, now what we do is, so we take a look at our ion list and we find that the magnesium ion is Mg2+, and the hypochlorite ion is ClO with a 1- charge on it. Okay, so I can take a look here and I can say, okay, this 2 needs to come down and the 1 needs to come down. And I'm going to need parentheses here. So this becomes MgClO2. And that means that there are 2 complete hypochlorite units. Let's think about another one. Let's do ammonium sulfide. Okay, and we look on our ion list and we see that ammonium is NH4 plus, and sulfide, be very careful here. We have sulfide, sulfite, and sulfate. So there's a bunch of them. There's also hydrogen sulfate as well. So there's a whole bunch of those sulfur compounds, but sulfide alone is just S2 minus. Okay, that S2 minus means that we need 2 ammonium units. So this becomes NH4 2S. And you'll notice that there's nothing in the name. This is never going to be called diammonium sulfide. You're never going to have magnesium dihypochlorite. There's no way of knowing how many of each thing you have in your ionic name. You always have to sit and think about it based on the ions. And in your recitation, I will be requiring you for everything, whether you're going from formula to name or name to formula, to identify the ions involved. And that's really going to help with that. Okay, so now let's take a look what happens when we have molecular compounds. So remember that a molecular compound contains no metals. Okay, and the one is sometimes omitted, usually if it comes first. Sorry, the number is always omitted in the formula, but mono is omitted. So we're just going to change this to always. Omitted if first. Okay, so here we have mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. Okay, so when we do, you need to know these. Okay, don't get them mixed up. Don't assume that you know them. Write them down and have them right next to you. Okay, don't try to look things up on a test. First of all, it's not allowed. Everything has to be in paper form next to you. Okay, so now when we do that, let's take a look at some things. For example, we know this is water. What else could this be known as? Well, do you see this dot, this 2 here? This could be known as dihydrogen monoxide. Okay, let's say that we have CO2. And again, there's a 2 there. So now we have just carbon dioxide. Let's look at, remember at the beginning, we looked at benzene, C6H6. Okay, well, this is called benzene. That's its common name. And in organic chemistry, it's going to be referred to as benzene, but you've got those 6s there. Okay, so here in general chemistry, we could call this hexacarbon hexahydride. Okay. Okay. So now let's take a look. Remember I said we were going to add one thing at the end of that, and those are hydrates. Ooh, hydrates. A hydrate is a compound. It says often ionic. We're only going to look at ionic hydrates in this class. It contains one or more water molecules bound within its crystals. Okay, so to name hydrates, first you name the anhydrous compound, and that part, the anhydrous compound is right here and right here, using the usual rules. And then you add the word hydrate with the Greek prefix denoting the number of water molecules that are complexed with it. So here you have CuSO4. Now, in order to come up with copper sulfate, what you need to do is you need to say, well, my sulfate is SO4 with a 2 minus charge. If I have only one copper balancing out that sulfate, then this must be Cu2 plus. And that's how you work backwards to identify that it's copper 2. Next, you'll see this 5 here with the waters, and that goes with penta. So copper 2 sulfate pentahydrate. Okay, now let's look at the bottom one here. Okay, so we know that chloride is Cl minus, and we know that calcium is Ca2 plus. It's right there, our monatomic cations. And this perfectly balances because we see that we have 2 negative chlorides balancing out our calcium. So then we have calcium chloride, okay? And now we have a 2 here. So it's a dihydrate. All right, now we're going to be looking at binary molecular compounds. So let me see, where am I? Okay. Now, I feel like I did this just a little bit ago. Oh, I'll just review this. I accidentally did this slide back when I was naming the prefixes. Molecular covalent compounds are used during a different set of rules. This one is exactly like what I showed before. So I basically covered this slide in slide 42. Okay, now let's take a look at acids. Ooh, acids are tricky. Okay, let's take a look here. Binary or simple acids do not contain oxygen. Right? They are formed when an H plus is combined with an anion that does not contain oxygen. Okay, so most of those are going to be your common monatomic anions like chloride. Okay, so so you'll start with hydro and then the anion root and then ic acid. Okay, so the ic acid here, acid means H plus out front. This hydrogen, if you see hydro here, this hydro doesn't mean hydrogen, it means that there's no oxygen in it, okay? Okay, so first of all, let's make an acid with the chloride ion. What's the chloride ion? Cl minus. And we're going to balance it with protons. So we have an H plus and a Cl minus, and those balance completely for HCl, which gives us hydrochloric acid. Now let's do the same thing with the fluoride and sulfide ions. Well, here's fluoride, F minus, and here's sulfide, S2 minus. And so we start by figuring out how many of these H plus or protons that we need to put on it. Well, fluoride is just a 1 minus charge, so these balance just as is, HF. There's no oxygen involved, so this becomes hydrofluoric acid, hydrofluoric acid. Hydrofluoric acid is really interesting. You're going to find out later when we're talking about acids that hydrofluoric acid is actually a really pretty weak acid. It's really strong. It doesn't dissociate. It stays stuck together. And you think, okay, well, that means it's safe, right? Hydrofluoric acid is one of the most dangerous acids out there, even though it's so weak. And the reason for that is that when you spill it on yourself, it will burrow through your skin, not burning you until it comes to your bones. When it comes to your bones, it will swap out the hydrogen for the calcium. Oops. And it'll decalcify your bones. So it's a really, really awful thing. The reason we know so much about how awful it is that it is a main component in the creation of semiconductors or computer chips. So if you've ever worked or will ever work in a semiconductor or a chip company, you will be well schooled on the dangers of hydrofluoric acid. If you ever work in a hospital in a town with a semiconductor company, then it's really important to understand how dangerous hydrofluoric acid is. You actually treat it with a calcium cream if it's just lightly on your skin. If you spill a lot of it on you, they will actually give you calcium injections. So no fun. Okay, but then H plus S2, well, we're going to need 2 of our protons to balance out that 2 negative charge. So this becomes H2S or hydro. Now this sulfur is weird. It doesn't become hydrosulfic acid. It's just hydrosulfuric acid. All right, now let's take a look at naming oxyacids. So again, you're always going to have that proton, that H plus out first. They're composed of hydrogen ions with polyatomic ions that do contain oxygen. Okay, so to name oxyacids, first we have to we start with the root name of the anion, and then you replace ate with ick or ite with us. Okay, well, what does that mean? Let's take a look here at what we're working on. So it says make an acid with the nitrate ion. So see how we have that 8? So it's going to be this one here. Okay, the nitrate ion is NO3 with a 1- charge on it. We balance it with protons, H plus balances evenly with NO3. So we have HNO3, and nitrate becomes nitric acid. Let's take a look at another one. Let's say that we have sulfate. Sulfate is SO4 with a 2- charge on it. When we combine it with an H plus, we'll need 2 of those. So that becomes H2SO4. And so we take sulfate, 8-ic, and this becomes sulfuric acid. And again, sulfur does that weird thing where it tacks on the rest of the word. Now let's take a look at selenite. Okay, and you'll see here we have selenite. So this one ends in ite, and we'll have that ite to us. Selenite is SeO3 with a 2- charge on it. When we balance it with protons, we'll need 2 of them. So we get H2SeO3. Selenite becomes selenous acid. Well, here we did nitrate. Let's take a look at nitrite. Nitrite is NO2 with a 1- charge on it. We balance it with protons, and they balance evenly, HNO2. And so the ite becomes us, and we end up with nitrous acid. Okay. Nitric acid, HNO3, very, very strong. Nitrous acid, HNO2, significantly weaker. So you can see how we have to be very, very careful with what we're doing here. Okay, so now what we're doing is we are getting into, this is the first slide that will be in our practice slides. So remember, work through these on your own. They are your homework, but they're not homework that's necessarily required, but work through them. And before the test, if you are taking an in-class class with me where we're in class, we will be working these in class, and you'll be able to work them and check your answers. If you're taking this as an asynchronous online class, once you're done with it, send me a picture to let me know that you did it, and I will send you the answer key. I will also post the answer key shortly before the test so that you can check those on your own. With this one, all you're going to be doing is, I'm just going to go through them quickly to kind of let you know what some of these are. So in this case, we're going to be, all you need to do is notice how many you have. So you have 1 carbon, 2 oxygens, 2 carbons, 4 hydrogens. Just try to come up with an empirical formula that will describe these, both empirical formula and molecular formula if they are different. Okay, now on this slide, you need to give the name or the formula. So in this first column here, use your ion list to come up with names. Okay, and here use your ion list to come up with formulas. And that's not real clear, but use your, what all I mean is here, take the formulas and use your ion list to come up with names. In this one now, we're going to be looking at what happens when you have those transition metals or those type 2s that I mentioned. These are often called type 2s, okay? And again, use your ion list to come up with a name or a formula. In this slide, you will be naming molecular compounds composed of 2 elements. And remember, for this, you need your prefixes, okay? In this exercise, you're going to be identifying, is it acid, ionic, or covalent? If it's acid or ionic, list the ions and then name each compound. In this one, you'll be using your ion list, okay, in order to find other things. So this is kind of a mix. So you'll notice we have an ionic compound. I'm actually going to help you here. Oh, look, here's an acid, gallium phosphide. Ooh, ionic compound. Okay, so most of these are ionic compounds with a few acids tossed in. So I just identified them there for you to kind of help you with that. And remember, if it's ionic, it contains a metal. If it's an acid, actually, we could say, instead of ionic, we'll say it starts with a metal. If it's an acid, it starts with hydrogen, or it starts with H+. Now we have a mix here: chlorine dioxide, dinitrogen tetroxide, potassium phosphate. So while you're working on this, one of the things you need to do is, again, let's start looking at this. This one has no metal in it. Okay, so while you're doing this one, what you want to think is you want to think about the rules. Are you ready? So here's our clues. Okay, if it is ionic, it starts with a metal or ammonium. If it is covalent, it has no metals, and that means it'll also have prefixes. If it is an acid, it starts with H+. And lastly, to remember, whoops. If it is a hydrate, it ends with H2O. So it's an ionic compound. It's an ionic compound plus water. And if you can't make this little dot here, some computer programs you can make it, in some computer programs you can't. You can put a plus sign instead of a dot in there. So let's say that you're trying to write calcium sulfate dihydrate. You could write dot to H2O, or you could write calcium sulfate plus to H2O if you can't make the dot. All right, now with these, you're going to be naming them, okay? So, and remember our clues. Okay, now here we have our last one here, and this is a weighted average problem. And you can refer back to what we did on slide 24 in video number 1 if you can't remember how to do that. And we are done. Good luck, and I will see you either in class, or if you need to talk to me, remember that I am always available to Zoom with students if you need me outside of class, or if we're taking an asynchronous class, send me an email with 4 possible times within the next few days, and I will get back to you usually within a few hours to set up a Zoom. Awesome. Good luck.